Okay, in this video we're going to solve some trigonometry problems using circular reasoning, and that's a bit of a pun, and we'll see exactly what I mean by that here in a moment. In order to do these problems, you will need a few supplies, just a few. You need a compass, a pen or a pencil, both maybe, and then some kind of straight edge. Now I use a ruler, but you can use really any straight edge. The demarcations don't really matter. And you probably need a calculator of some kind. Those frequent viewers of this channel know that I tend to not like to use calculators for these problems, but in some cases when we actually need to compute the sine, cosine, or tangent, which is actually less often than you might think, the calculator can be a useful tool. Alright, so let's clear our workspace and consider a problem. For those of you who are working on a homework assignment associated with this video, I am going to work problem 1. Okay, so we're given a right triangle, and we are given side lengths, and we're asked to find the angle, find the missing angle. Well, not only are we going to find the missing angle, but we're going to find the opposite side here as well. This is the answer key. I'm always trying to reinforce this to my students that, first of all, here is the answer. So if that's what you thought we were doing with this assignment, here it is. All right. What I'm really interested in is what thought process went into finding this thing. But I don't see any point in denying the reward of checking to make sure you're correct once you solve it. So there's the answer that we're hoping to find. And that'll really be a demonstration of whether everything I'm saying is total nonsense, which is also more often than you think. Okay, what I'm going to do on this work surface right here is recreate the picture we just saw so we can work with it a little bit more. And to do that, I will use a pencil. Get my pencil sharpener out. With these problems, it often kind of baffles students where to start, with these problems. And the first step in pretty much every trigonometry problem that you come across, at least until you get into calculus, the first step is to draw something. So I always tell students, think of trigonometry as kind of an art class with mathematics. And it'll be a little bit more fun in addition to being helpful. Okay, so now I've got a pencil that's sharp. I really like these pencils right here. This is actually the brand of pencil that was owned by Henry David Thoreau back in the 1800s. These two companies merged. I think Henry David Thoreau's family owned American Pencil Company. But anyway, it's a hard lead, and it's a hard wood. It's not soft like the Ticonderoga pencils. Anyway, so let me draw the triangle. I want to draw this triangle large enough that you can see it, but small enough that I can put a whole circle around it. So this is kind of what I'm looking at here. The angles don't have to be perfect. You know, we're just going to indicate that that's a right angle. There's no need to get out a square to make it exactly perfect. And here is our angle theta that we don't know. Okay, so there's theta. We are given this side length of 12. No units are provided, so we'll just call it 12 units. And then we're given this side length of 13 units. Okay, since that's not showing up very brightly, let me switch to pen. Because if I decrease the brightness, the field will look real dark, so I'll just switch to pen. Okay. First things first, I need to draw a circle. So with the compass like this, you can take out the pencil and put in something else. And I'll put in a pen. Okay. All right, and what we want to do is open up our compass to be the distance from the observation angle, which I'll talk about in a moment, and the hypotenuse of the triangle, which in this case is right here. Now, as I've stated in a previous video, this hypotenuse of this triangle is actually the radius of a circle, right? And we actually know the radius of a circle now, because if you see, if that is in fact true, then that right there is the radius of a circle. So this hypotenuse length of 13 is the radius of a circle. I want to dwell on that for a moment, and we'll come back to it. Okay, but first, just draw. Before we calculate, draw. Right? Oops. There we go. So now we have a circle of radius 13. I think that drawing the circle helps visualize this more as a radius than as a hypotenuse. A lot of times in your head you get to thinking of a triangle and you can't think visually of the circle, but this is the center of the circle right here. Okay, there's the edge of the circle right there. And what we're interested in is, you know, you call it trigonometry, but it's really just algebra and geometry of a circle and triangle, right triangle. So let's see what we can compute. Well, without any trigonometry per se, we can compute this side using the Pythagorean theorem. I said I was going to use a pen to do it, so let's use the Pythagorean theorem to solve for this side. Now to do that, I need to kind of arbitrarily call the 12a and the 13c. All right, and what I'm looking for is side B. Okay, and I need to recall that you know, the Pythagorean theorem states the Pythagorean theorem states that a squared plus b squared equals c squared. And by a couple of manipulations where we take the square root of both sides of this equation, I get, if depending on which variable I want to solve for, which in this case I want to solve for b, I'm just going to subtract a squared from both sides. And then I'm left with this secondary equation, b squared equals c squared minus a squared. Okay, so if I want b by itself, I take the square root of b squared and the square root of this entire expression to the right of the equals sign. Can't see what I'm doing. Okay, this would be a little bit better. Okay, and that gives me b by itself is equal to the square root of c squared minus a squared. Okay, so let's plug in what we have. We have 13 for C and 12 for A. So we need, we'll just come over here a little bit and say that B is equal to the square root of 13 squared minus 12 squared. Now, if you can't remember what 13 squared is, before you reach for the calculator, just try doing it the old-fashioned way. So 3 times 3 is 9, 1 times 3 is 3, 3 times 1 is 3, 1 times 1 is 1. So that's 9, 6, and 1. So 13 squared is 169. 12 squared is 144. 12 times 12. It's always good to remember how to do basic math. So 169 minus 144, there's another math problem we can do. 169 minus 144. Okay, that's 5, 2, 25. Okay, 44, 54, 64 plus 5, 69 makes sense. So we're really looking at the square root of 25. So b equals the square root of 25. Well, what times what equals 25? 5. So the square root of 25 is the same thing as saying b equals the square root of 5 squared. Okay, so b is equal to really plus or minus 5, but we're only taking positive values, so b is equal to 5. Okay, so I didn't need a calculator, is what I'm trying to tell you for this one. The problem worked out nice and neat, so b equals 5. Okay, so a is equal to 12. The radius or hypotenuse of the triangle is equal to 13, which is C, and then b is equal to 5. That's that short side. For the purposes of this exercise, we will also refer to b as the opposite side. I'll explain what I mean. And we will refer to a as the adjacent side. Okay, so we're referring to C as both the hypotenuse and the radius. Okay, so many people will be smashing their head against the monitor right now saying, oh, just use the inverse of one of the trigonometric functions to find the missing angle. But what if we don't remember that? What if we don't know that? Is there anything we can do to find out what this angle is? Well, maybe. Let's see. We know that this is 13 units right here. Okay. We know that the height is 5. We know that the base of this triangle is 12. So let's think about what we do know. So this opposite side here is opposite with respect to the angle that we want to know. Okay, so I call this the reference angle, and this is really, I put a little eyeball there. This is what I'm looking from here out, and so this is my reference angle. So what's opposite of my vantage point, more or less, is what's going on there. So the opposite side from this reference angle is the sine, okay, of the angle. So this distance right here is actually the sine of theta multiplied by the radius of the circle, okay, which is actually 13. And we know that that equals 5. So I'm actually going to be able to find out what the sine of theta is. This might help me later. Okay. Similar to that, the cosine is the base of the triangle, and so that would be right here. This distance right here this is actually called the cosine of theta multiplied by the radius value. Okay, what we're really doing is scaling up from the unit circle of radius 1 to a circle of radius 13, but nothing else changes really. It's really a scaling up factor. So if we know, let me show you what I mean. I'm really scaling up from a much smaller circle. So this isn't to scale at all, but I'm scaling up from a smaller circle. I'm scaling up from a small circle, which we call the unit circle, where the radius is equal to 1. I'm scaling up to a radius of 13. That's really all I'm doing. I'm scaling up like that. So let's keep meditating on this, see what we can't, if we can't find something out. Let's think for a minute. If we wanted to know the area of this whole sector, right, I would need to know the angle, and I would need to know the radius, because if I wanted to know the area of the sector, I'll put it to you this way: the area of the sector is equal to theta degrees, okay, divided by 360, multiplied by pi times the radius squared. In other words, it's a portion of the total area of the circle. So right away we're seeing how conceiving of these triangle problems as portions of a circle can be helpful to us. So again, I'm trying to get at this angle, and I'm trying not to use one of the inverse trigonometric functions to find it. Let's see if there's some other way to come at this. What I mean by sector is this whole area. So see if I can't highlight this. This whole area here. Is that coming up a little bit? This whole area is what I'm talking about. That's the area of the sector. Okay. So what can I do to find that? Well, I know what the area of a triangle is. So the area of a triangle is base times height divided by 2, right? Which we could think of as cosine theta times r times sine theta times r divided by 2. Let's write that down. So the area of the triangle is sine of theta times r times the cosine of theta times r divided by 2. In other words, this is the height. Okay, so I'll call this height. And we'll call this base. This is the height. Times the base. Divided by 2. It's the same triangle formula you've been using forever. Okay, so we're making some progress. Let's see if we can't get at this angle a little bit. I know that the sine or height is equal to 5 units. We found that using the Pythagorean theorem. And I know that 5 units is equal to the sine of theta times r, which is 13. Okay? Just make that really clear. So if I want to know what the sine of theta is, I can divide out 13 on both sides. They cancel out on the right. And then I'm left with 5 divided by 13. Good time to bring in a calculator. What's 5 divided by 13? It's that huge number right there, or that really small decimal. So we'll call this, this is going to be a radian measurement, 0.3846153.846 radians equals the sine of theta. So again, what does it mean? Think about what it means for a minute. it's this distance, only on a smaller scale. So it's actually, what we just found is this little height right there. That is what we just found. So 5 is the scaled up version of that little tiny height right there. That's what we just found. The question is, what degrees are associated with that height? So that's the distance right there. And what I'm really trying to get at is, I want to know what this angle is right here. I want to know what the angle is right there. I want to know what the angle is right here, theta. And so I want to know the radian measurement from here to here and here to here. So I'm just trying to see if anybody's catching on to what I'm trying to find. Okay, let's keep going. So the cosine, stick with me, the cosine, or base, is equal to 12, which is equal to cosine theta times 13. Right, so let me divide out 13 on both sides, and I get 12 divided by 13 because these cancel. Let's do 12 divided by 13. We get 0.92307692231 equals cosine of theta. Okay, so I've got these two data points here, and this is in radians. So for a unit circle of radius 1, this is my height when r equals 1, and this is my base when r equals 1. Okay, let's zoom in on this triangle here for a minute, or this in this smaller circle. Let's make a little bit of a larger circle down here. This will be our unit circle blown up. So this is my unit circle, and I will draw in what we know. So now we know that the radius is 1. Okay, and it's about the same angle. Okay, and then I'm going to draw it. Okay, so this distance right here, this distance, it's really important. I don't want to clip this last little piece here. This distance is the cosine of theta. So this is the cosine of theta. And this distance right here, this is the sine of theta. Okay, now we computed those values. They're right here. Here's the sine, here's the cosine. Okay, in radians. So now I want to find the area of this circle. Triangle, rather. I want to find the area of the triangle. It's going to come back up here to the sector thing here in a minute. All right? What is the area of the triangle? Well, the area of the triangle is the base times the height divided by 2. If the base is the cosine of theta and the height is the sine of theta, then I just need to multiply the cosine of theta times the height, or the sine of theta, okay, and divide that by 2, which gives me the area of that tiny little triangle. Okay. So the area of the triangle for r equals 1 equals 0.17751479929 units squared. Okay? And what I'd really like to know is, what is theta? Okay. Well, I don't know what theta is, but I do know what the radius is. I know pi, I know 360. So can I solve? So here, this is equal to area of the sector. Well, not really, because I don't know the area of the sector, and I don't know theta. So I've got two variables there. Can't quite solve yet. I do know r. Is there any way that I can approximate the area of the sector? Sure. I can approximate the area of the sector by looking at the area of the triangle, because the area of the triangle almost takes up the entire area of the sector. Only this little piece is missing right there. So it's a good approximation. I know that my area of the sector is going to be a little bit more than this. All right, so let's see where we are with this area. Let's see where we are. Let's go back to our formula. So if I'm going to now plug area of sector, I'm going to plug in the area of the triangle. And I know that this isn't right, but it's going to be an approximation. We could do something like this. Approximate area of sector equals the area of the triangle with the radius equal to 1. Okay, so that would be my plug value for area of sector. Right, r is 1, so I really have this degrees that I don't know, divided by 360 times pi is equal to 0.17751479929 units squared. Let me show you what I mean by that. So 0.17751479929 units squared is less than, right, because I know that the area is not correct, so it's an inequality, is less than theta degrees divided by 360 times pi times the radius, which is 1 squared. All right? So we're going to try to solve for the degree symbol right here, theta. What would I need to do? Well, that's 1, so he can be forgotten for a moment. The first thing I want to do is get rid of pi, so we'll just divide him out of both sides. Divide out pi. And then multiply both sides times 360. Okay, so what I want to do is multiply 360 times that divided by pi, and that will give me an approximation. It'll be too small, but it'll give me an approximation of the angle. Let's see what we get. I'm curious. So I'm going to take 360 times that area, okay, enter, divided by pi. And so what I get is 20.341696 degrees. Okay, is less than theta. All right, so I need something bigger than this. But it does give me some basic idea of what the degree measurement is for theta. I think it's interesting that we can even come close using triangles. And you know what I could do in order to narrow in on that if I wanted to, using approximations, is try out angles and see what I get for the sine and cosine. You know, like you could play this game, right? Trial and error. You could say, well, if the sine of theta is, if theta is a little bit bigger than 20, you know, within 5 degrees, it wouldn't take you too long to try all the values unless it was some weird angle. You could get pretty darn close. You know what the sine equals. The sine equals 0.3846, right? So you could take the sine. If we're going for 0.3846, you could take the sine of 21 degrees, assuming you're in degree mode. Yep. And you get 0.35. Okay. Remember, I'm looking for 0.384. I could take the sine of 22 degrees. Okay, 0.374. How about the sine of 23 degrees? 0.39. It's too big. So I know it's somewhere between 22 and 23 degrees. So I could take the sine of 22.5. Let's see where that gets me. 0.3826. How about the sine of 22.6? 0.384295327. How about sine of 22.4? No, I was closer before. Sine of 22.5. 22.66.385. How about sine of 22.64? Sine of 22.63. Okay, I don't know. We're zooming in on it, aren't we? We're getting close. Now, the way that you really find the angle is once you know one of these sides, you can find the angle. Like, the way this works is you use the inverse sine, inverse cosine, and inverse tangent functions. So, for example, you know that the sine, put it to you this way, the sine of theta times r is equal to 5. Okay, and 5, this 5 right here is equal to the opposite over the hypotenuse, or 5 over 13 is equal to the sine of theta times r, which we know. We know that r is 13. So if I substitute in 13 there, you can see how I can cancel these 13s out. Okay. So the sine of theta times 13 is going to be 5. So sine of theta times r equals 5 over 13. 5 divided by 13. There it is, 3846. So if I want to know what the angle is given these length measurements, I take the inverse sine of 5 over 13. And it gives me 22.61986. So here, theta is given as 22.61986 degrees. Given this information, we can now compute the area of the sector, right? Because we know theta now. Theta has a value of 22.61986 degrees. Okay, so if I want to know the area of the sector, I'm just going to follow this formula here and say 22, well, let's use their value, divided by 360 times pi times, open paren, r squared, or 13 squared. So the area of the sector is equal to 33.35984 units squared. Okay, and so like a question we might want to ask is what percent of the entire circle is taken up by this sector? And we can answer that question. We could also answer that question by saying, well, what is the total area of the circle? So the area of the circle is equal to pi times the radius squared. So the area of the circle here is equal to pi times 13 squared, which is equal to pi times 169. That's the total area of the circle. And so if I want to know what percent of the circle is taken up by the sector, I could just divide the area of the sector by the area of the circle. So I could write over here percent area circle taken up by the area of the sector equals the area of the sector divided by the area of the circle. Okay, which is equal to, the area of the sector is 33.35984, okay, units squared, divided by the area of the circle, pi times 169. Let's see what we get there. So we'll grab our, and then divide that by open paren pi times 169. And it says that this sector is equal to 0.06283, whatever. Call it 33. And then it says a percent, that's equal to 6.2833%. I think that's interesting. Was there any other way to come to that conclusion? Well, our angle measurement is 22.61986 degrees. So what would happen if we take that angle measurement and divide by 360? I get the same thing. So I didn't, another way to find it is just to take the angle and divide by the total number of degrees in a circle. So your angle degree divided by the total degrees in a circle will give you the percent that circle, that angle inscribes, and it inscribes 22.61986. Now here's an interesting question. We know the area, we can find the area of this triangle is going to be equal to 12 times 5, which is 60 divided by 2. So the area of the triangle in here, this area, 12 again, 12 times 5 base times height divided by 2 is equal to 60 divided by 2, which is 30. Okay, 30 units squared. And we know the total area of the sector, right? So we know that the area, so I want to know, I'm curious, what is the area of this shaded region here? In other words, the area that's not in the triangle but is part of the sector. So I could just take the area of the sector minus the area of the triangle and that would give me the area of the shaded region. Right? So what are those values? The area of the sector is 33.359. Here we go. There's the area of the sector, and the area of the triangle is 30. So the area of the shaded region is 3.35984,962 units squared. Okay, and so we could even find what percent of the total area of the circle is taken up by the area of the shaded region. We could also find what percent of the sector is taken up by the area of the shaded region. That might be interesting. So let's take that and divide by the area of the sector. 10%. So our error margin by using the triangle as a close approximation of the total area of the sector was off by 10.071%. You know, it's the point I'm trying to make is that we have spent several minutes now, close to an hour really, just musing on the all the different things that we could do with problem number 1. And it was, in my opinion, so much more fun than merely computing the answer as quickly as possible. I feel like we miss something when we rush to answer. And when you're through, if I could zoom in or zoom out a little bit, see if we can't get all of this work in frame. I'm not sure that I'll be able to. Kind of filled up a page here with mathematics that I'm trying to get at. Yeah, there's the whole page. And, you know, we'll call this lesson, I guess, right triangle trigonometry, right triangle trig, colon, circular reasoning. The whole purpose of this lesson was to demonstrate how conceiving of these triangles as circles can give us insight that would otherwise be unavailable to us if we were merely focused on the computation of the one thing we were looking for, which was that angle. I mean, that was the thing we wanted. But instead, we had a lot of fun. And, you know, I encourage you to spend that much time musing over all of these problems on this little worksheet. I mean, I found this worksheet online. It's really, with all this work in mathematics, it's really supposed to be a fun adventure that you take with each problem. You know, we had a little fun with it, and there's just no need to rush through. As we've seen here, one problem can teach us innumerable skills and reinforce things we already knew, give us a way of looking at things in a new way, and have fun doing it. This is the unit circle. Oh, you know, one thing we never computed were these radians. So we can actually compute this sector length, right? Now that we know what the angle is, 22.6. See, let's go back to our unit circle here before I close. The radian measurement is the sector length of this angle. Now, radians equals degrees times 2 times pi times the radius divided by 360. Right? If the radius is 1, then I just need the degrees. So the radian measurement for a unit circle of radius 1 is, given our angle here, our angle measurement was 22.61, whatever, times 2 times pi, okay, divided by 360. And so the radian measurement for r equals 1 equals 0.3947911197. That was 0.3947911197. Okay, that was for radius 1. So that was the radian measurement of 22.61986 degrees. For the larger circle, if I actually wanted to know what this arc length is right here, then I'd just do the same thing, right? So for r equals 1, how about for r equals 13? Okay, same degree, just use that, go back there and then multiply that times 13 and divide by 360. So that sector length, right, this sector length right there is equal to 5.1322845557. Okay, and this is like a portion of the circumference, right? Well, what's the total circumference of the circle? So the circumference is equal to 2 pi r, right? So the total circumference is equal to 2 times pi times 13, and 2 times pi times 13 is equal to 81.681408899. Okay, so my question is, what percent of the total circumference is taken up by this arc? Let's see. Take that and divide it by the total circumference, and we find 6.2833% again. So this keeps coming up, right? So I could have used that, right? If I knew the total circumference, I could find this. As a matter of fact, now that I'm thinking about it, we didn't need to use the arc sign, did we? Because I wanted the angle, right? So I already knew that this was 13. Let me see. Did I need that or not? Yeah, I did. I did need the angle in order to compute what I just did. Yeah. Okay, just showing you that it doesn't matter if you're computing the arc length here as a portion of the total circumference of the circle, or if you're computing the sector area as a portion of the total area of the circle, the percents are going to be the same. I think this light flickering out is probably a good indication that I should stop recording. That's kind of neat to figure out what's going on there.